Hello, I'm Simon Engler, and today I'm talking about a project I did for my Computer Science 230 Deep Learning course. Title of my project is the MASC or CNN for Exoplanet Candidate Stellar Companion Detection. And this project attempts a novel application using a mass regional convolutional neural network to adaptive optics observational data from exoplanet candidates from the Kepler telescope. We found that anomalous light curve behavior observed create inflated exoplanet radii measurements and false positive exoplanet detections. The high volume of stellar observations cannot possibly process manually and require intelligent software to conduct the task. Effectively, we're taking stars that the Kepler telescope has observed and believes there's an exoplanet around them, and then re-observing the star from a high-resolution adaptive optics telescope here on Earth, where uh, we then examine for potential companion stars around the detection area that the Kepler telescope couldn't see. And if there's a star, a primary star, there may be a secondary star or a third star in the field of view, which would skew the observations. Starlight, uh, because starlight is collected on a charge coupled device, which you can read about here, and we needed to simulate starlight in various situations as the number of companion stars within the data set is relatively small. However, the it was necessary to simulate a number of situations for the training data. The MassCRNN combines segmentation, semantic segmentation, which assigns a class to each pixel in the image, and object detection, which creates object bounding boxes. And then instance segmentation is applied to each pixel that combines the bounding boxes and classes to create a mask to place over the object. The MassCRNN RNN is built upon a fast CRNN, which consists of a convolutional neural network, a region proposed network, and a classifier. The mass CRNN will use the output of calculate the probability of an object within the bounding box at each pixels. And for each for the training set, we needed to annotate and create annotation for box prediction. So we use software to annotate stars and all the images and classify them as a primary or a secondary star or a field star. And on the real images, the bounding boxes, we're able to use the annotation to locate the stars. Then after the bounding box training, we went to mask generation, and rather using bounding box coordinates from the data set, the bounding boxes are computed from the masks. This allowed for more consistent handling the bounding box despite the data source. And also, what's is important here, this provides a very high measurement of the flux of the stars and allows for extremely accurate corrections to the light curves. Thank you for your time.